We're going to start studying Chapter 10, the ideal spring and simpler harmonic motion. The picture here shows a spring that can be both compressed and expanded, and this is the type of spring we're going to be discussing for the most part here. You'll see it has an unstrained length right here. A certain force is needed to stretch the spring a certain distance x, or that same force is needed to compress that spring a certain distance x as well. Here is a demonstration of taking a mass, let's say 250 grams, putting it on a spring and letting it hang on the spring. Now, I don't want it to bounce up and down yet. We'll talk about that later. We're just letting the spring stretch. And you'll see that it's stretched about 10 centimeters with a 100-gram mass. And if I put another 100-gram mass on there, let's do it this way. Let's take this 100-gram mass off. And then if I put a 50-gram mass on there, it's going to stretch about half the distance. Okay. Now, some springs are stiffer than other springs. We take this 100-gram mass and put it on here, and this 100-gram mass put on here. Stop. We see from this that this spring 3 is a looser spring. Its spring constant, we're going to call it, its spring constant is less. It's a looser spring. This is a stiffer spring because this one stretches further. The equation we're going to learn is for an ideal spring, we base the equation F applied equals Kx, where F applied is the force applied to the spring, X is the displacement of the spring, its unstrained length, and K is the spring constant. So the equation looks something like this, F equals Kx. And here's an example. In a tire pressure gauge, the air in the tire pushes against a plunger attached to a spring. The gauge is pressed against the tire valve. So here's our spring that's being compressed. Suppose the spring constant of the spring is 320 newtons per meter, and the bar indicator of the gauge extends 2 centimeters. When the gauge is pressed against the tire valve, what force does the air in the tire apply to the spring? So our X value here is the 2 centimeters. Our force applied is from the air. All right, we want to solve for that force. So of course we're going to use that equation F equals Kx. Plug in our values, 320 newtons per meter times 0.02 meters will give us 6.4 newtons of force were applied on the spring. And here's another example. It says here figure 10.3a shows a 10-coil spring that has a spring constant K. If this spring is cut in half so that there are 2 5-coil springs, what is the spring constant of each of the smaller springs? And since each coil itself compresses a certain amount, if you have 10 coils, you'll compress a certain X value. But if you only have 5 coils, you can only compress with that same force applied. It'll compress half the amount. So the spring actually becomes stiffer. It becomes twice as stiff as the 2 coils. So that's what this says right here. In general, the spring constant is inversely proportional to the number of coils in the spring. So shorter springs are stiffer because they have less coils. Each coil only can compress a certain amount. So if you have less coils, there'll be less compression. Here's a different type of problem we'll encounter. It says here a 0.42 kilogram block is attached to the end of a horizontal ideal spring and it rests on a frictional surface. The block is pulled so that the spring stretches by 2.1 centimeters relative to its unstrained length. So that's its X value is 2.1. When the block is released, it moves with an acceleration of 9 meters per second squared. What is the spring constant of the spring? Okay, I've set this situation up here, so the spring will not be moving due to gravity. This spring is a horizontal spring. So for instance, when I put the spring on here and let go, it will not drop down. It won't move at all. There's no gravity acting downwards on it. This is a horizontal spring. So what I'm going to do is I'm going to pull on it, let go, and you'll see right away it starts to accelerate. The greatest acceleration actually happens at the end points zero acceleration occurs in the middle. The acceleration is always changing, but we have this acceleration occur. So that's the picture for this problem, so that this thing is now accelerating at 9 meters per second squared. Well, we know that we have F equals kx, but we also know that we can use F equals ma at the same time. So we have F equals kx and F equals ma. We can set those two equal to each other. And when we set those two equal to each other, we get kx equals ma. Plug in our values, and end up with a k value of 180 newtons per meter. This motion that we just discussed is called simple harmonic motion. Whenever you pull on an unstrained spring and let it go, it'll move back and forth in simple harmonic motion. And watching this move up and down, here's an example of an object in simple harmonic motion. When something's in simple harmonic motion, it actually corresponds to a sine curve. By attaching a pen to the object, we use to paper pass at a steady rate, we can record the position of the vibrating object as time passes. The maximum excursion from equilibrium is the amplitude A of the motion. The shape of this graph is characteristic of simple harmonic motion. So we have this spring moving back and forth in simple harmonic motion. You'll see this dot right here follows the mass of the spring. It moves up and down in a sine curve, or you could call it a cosine curve. Either one's fine. There's some interesting things you'll see. If I were to put the velocity vector on this, you'll notice that the velocity is the smallest at the ends, and it's the largest in the middle. And look what happens with acceleration. It actually is opposite of that. It's the largest at the ends, and the smallest in the middle. But anyway, this an object in simple harmonic motion draws out a sine or cosine curve. So here we have for a vertical spring, the weight of an object on a vertical spring stretches the spring by amount of B sub O. Simple harmonic motion of the amplitude A occurs with respect to the equilibrium position of the object on the stretched spring. So you let the object go in equilibrium, so it's resting right there. You pull it down a little bit, or you pull it down to the amplitude A, and it will vibrate back and forth across the equilibrium position of the amplitude A. The same thing will happen on a horizontal spring, but you won't have this weight pulling it down at distance dO. What you would have is you just pull on this ball from here, and the equilibrium position would be right here. So here's a horizontal spring that this would move back and forth. Here would be your equilibrium position, and this distance here would be your A. They call it X here because it's just a certain distance away from the center position, but the maximum X value is the amplitude. So here we have another situation where we are going to show a displacement versus time graph. I'm going to pull down on the mass, and you'll see that we actually start with a sinus. It depends where you start, whether it's a negative sine curve or a negative cosine curve like we just had. Just move up and down, you'll see that the path corresponds to a sine curve or sine or cosine curve. If I do velocity, let's see what happens. Velocity, when it's at its maximum, the velocity is 0. It's at the velocity is at its maximum. I'm doing an acceleration curve in here as well. So what we've learned is how to calculate the spring constant using F equals kx. We also have learned what simple harmonic motion is and how it corresponds to a sine curve. And we've also looked at the velocity and acceleration of these curves.